All right, so we're looking at Le Chatelier's principle today. We're going to be looking at how disturbances affect the equilibrium and which way they will proceed to get back to equilibrium. There are three things that can be disturbed here: the temperature, the pressure, or the concentration of the system here. So that's what we're looking at. Here are the lovely learning targets. All right, so basically here I put the definition in your notes so you didn't have to write it. This is the quoted definition of Le Chatelier's principle. Systems at equilibrium, it's disturbed by a change in temperature, pressure, or concentration of one of the components. The system will shift its equilibrium position to counteract the effect of the disturbance. So that's basically what we're doing here. We're going to be looking at it. But as always, the lovely animation video is good, so we're going to take a look at that. Has the particulate model diagrams in it, and we definitely need to be able to count those and manipulate those and look at them always from our chemistry concepts. Okay, so in the animation you saw, he goes into the Haber process, which I use that example throughout this particular notes because it has different moles for all of the components and things, so it's definitely a good example. And we're going to talk about all of those things in detail, but as you can see, when they were disturbing it, how the different particles were changing, and that's what's going to happen here. All right, so concentration, these are general terms. If you add to one side, it's going to go to the opposite side, basically. So if you add to the reactants, it's going to proceed to the products. You add to the products, it's going to proceed towards the reactants. However, if you remove a component or a chemical species, it's going to go to the side that it was removed from. So it's going to replace what has been removed, basically, is what we're going for there. So these are general ways of thinking about it. Now, you wouldn't use this as an explanation because this really doesn't represent why it's doing what it's doing, but this is just the general trend. So when we're talking about concentration, adding stuff in, adding in gaseous or aqueous reactants that will proceed right towards the products. They told us to stay away from the word shifting a long time ago, about 4 or 5 years ago. However, I don't think there's anything wrong with it. It's in the definition for Le Chatelier's principle. You could say it shifts right towards the products. But when you're explaining when you add stuff or remove stuff, you do need to do the QK relationship. So you don't necessarily have to do this part where you're like showing that part. But if you add reactants, you're adding to the denominator, which is going to make Q less than K. K is going to be greater than Q, so we know it's going to go to the right. So definitely when you're looking at concentration things and you have to explain it and prove it, you want to do the QK relationship, explain that, why it's going to go the direction it's going to go. Adding gaseous or aqueous products, the reactants proceeds left towards the reactants, or you could say it shifts left towards the reactants, and once again, don't necessarily have to show the proportions, but the reason why this works is if the products are increasing, the numerator is now increasing, so now Q is going to be greater than K. And obviously, we write it with K first, it's going to point the direction of the shift, going towards the reactants there. Now removing. Okay, removing reactants, it's going to go left towards the reactants. So now we are removing, making the denominator smaller. You make the denominator smaller when you divide. You're going to get the bigger number. That is correct. So in this case, then K would be less than Q. So it is going to go towards the reactants. When removing products, same idea. Now we are removing from the numerator. Products is going down, still dividing by the same number. That means that your Q is going to be less than K. So it's going to go towards the products. So that's what's significant here. A lot of times in these questions, there'll be one in the free response where it'll ask which way is it going to go, and then you need to explain why. If it's an adding or removing concentration, make sure you put in the KQ relationship in your explanation. So practice here using our Haber process, nitrogen, hydrogen, and ammonia. So tell me which direction it's going to go. Okay, so if we add in nitrogen, which way is it going to go? Right towards the products. Good. Okay, adding in reactant, of course, is going to make K greater than Q. Q is going to be smaller, so it's going to go to the right. We add in ammonia. It's going to go toward the left towards the reactants. In that case, the K is going to be less than Q because you're adding in product. Now that number is going to be larger for Q. Removing nitrogen. Left towards the reactants. Good. You're removing a reactant, and this is where we get that the Q is going to be greater because you're making the denominator a smaller number. Removing hydrogen. Same thing because it's the other reactant as well. Very good. So you're removing another one that's on the denominator, and therefore going to make Q a bigger number than K. So they're citing the nice little reasons. All right. Now let's talk about changes with regards to temperature and heat. Going back to our types of reactions with heat exchange, we have endo and exothermic. Now what you want to think of them in this particular relationship as being part of the chemical equation. So endothermic, you actually put heat on the reactant side and treat it as though it is a reactant. And they could write in the word heat. They could also write in the word energy. They could put in like 100 kilojoules or something as they're adding it in. And that's going to designate to you that you know that that one's endothermic because heat is being absorbed, energy is being absorbed into the system. They could also do this where they give you the delta H and give you that next to it so you know delta H is positive, so you know it's endothermic. So also which direction to put the heat on. You got to know what side it's on in order to manipulate with Le Chatelier's principle. So delta H for exo is going to be negative, so if you see a negative delta H, or if you see the energy, whether it's written in kilojoules form or just the word energy or heat, you know that that's going to be an exothermic reaction. And since you know where it is, that's the side it's going to be on when you're going to decide which way it's going to proceed. Now, one other thing to note about temperature. Temperature changes K. The K number, the proportion number will change. Why that is has to do with kinetics. And we're going to get into more about the kinetics later, but basically what happens when you increase temperature. The average kinetic energy of the particles, in general, is higher. They're all moving faster. Now, basically increases the rate for everything. However, depending on where the heat is or whether it's endo or exo, which reaction is speeding up faster? Is the forward going to have an initially higher rate, or is the reverse going to have an initially higher rate? Eventually, they will stabilize and be equal rates again at the new position. But initially, which one speeds up faster is based on whether it's endo or exo. Now, also implied in the video too, talking about the Haber process and manipulating temperature to make sure that you get the most ammonia out of the process, that the Haber process being exothermic. So it is more advantageous to make it a lower temperature. However, if you decrease the temperature of the system, you're slowing down all of the particles. So their collisions will be less frequent. So it does slow down the reaction, as said. So the same will occur, though, if you decrease the temperature. The rate is going to decrease overall, but one of them, depending on whether it's exo or endo, will still be initially higher than the other, okay? Then eventually, after equilibrium is established, you have equal rates again, but it will not be at the same rate as it once was, depending on the temperature change. Endo, the forward rate is higher. You're going to have more products made, and your K is going to increase. So if it's endothermic and you're increasing the temperature, the forward rate would be higher. Now, if you're decreasing the temperature, the endo would be lower, okay? Exo, the reverse rate is higher, and you get more reactants made, so your K value is going to decrease. These two are referencing on here whether you're increasing the temperature. I said a lot of times increasing the temperature is going to speed up the overall reaction because it's making the particles have more energy, they're going to collide more in that respect. Okay? All right. Same idea as concentration. If you add to one side that has heat, it's going to go to the opposite side. Or if you remove heat from one side, it's going to go towards the side where the heat has been removed. But positioning where the heat is in the reaction is key here. You need to make sure that you have it written on the correct side so you know which way you're manipulating it. So if you add to one side, it's going to go to the other, shift to the other, proceed to the other. If it's removed, it's going to proceed towards the side it was removed from. All right, so this particular one, looking at our Haber process again, as you see, the heat is on the product side, as seen in the video too, so this one is exothermic. So go ahead and determine which way it's going to proceed and how that is going to affect K. Is K going to increase or decrease? So looking at an increase in temperature here, since heat is over here as a product, we increase temperature, which way is it going to go? So it's going to go towards the reactants. Very good. Towards the reactants here. Now remember, you can always reflect on your generalized equation here. If we're making more reactants because of the increase in temperature, that number is going up. What happens to our K value? K is going to decrease. Very good. Okay? And I guess that would go over here. Now, a decrease in temperature, which direction is it going to proceed? Right towards the products. Good. And also here, this time, the numerator, the product number, is going to increase. So what happens to our K? K is going to increase. Correct. The reverse reaction rate is going to be higher if it's proceeding towards the reactants here, because the reverse is a little bit initially higher when the temperature is increased. And then when we decrease the temperature initially, the forward rate is going to be higher until they get back to equal rates. And remember, like, increasing the temperature, the new rate, when it finally gets equalized at equilibrium, is going to be higher than the original rate. And if you decrease the temperature, the new equilibrium rate is going to be lower than its original equilibrium rate if you decrease the temperature. But you'll see there's a graph later on that will show this to you. You'll be able to visualize it a little bit better. The effect on K, yes, is increasing over there. All right, pressure. Number of moles, you have to count. So look at the moles of gaseous products and reactants. You need to count them before you begin to decide which way it's going to go. So increasing pressure proceeds to the side that has fewer gaseous moles. Decreasing pressure is going to go to the side that has more gaseous moles. Now, we also have the idea of Boyle's law in here because we can manipulate pressure by changing the volume. If you remember Boyle's law is P1 V1 equals P2 V2. So some of these questions will be formed in the idea of increasing volume or decreasing volume. So you can also see if you increase the volume, that means your pressure is decreasing because this is an inverse relationship. One other thing they throw in for AP is they might sometimes tell you they're adding in an inert gas. Inert gases are non-reactive, they do not react. So the ones that they'll be selecting to put in that kind of question would be a noble gas. Those ones are the unreactive gases. They do not affect the equilibrium position, so there will be no shift. Nothing will change about your equilibrium position. The only thing that the addition of the inert gas will do is it will increase the entire pressure of the system because you have more particles in there. But because it's not reacting with either side, it doesn't affect the equilibrium position. Okay, so count the moles. First, always start with the pressure by counting the moles of gas before you try to answer. So this side has a total of 4 moles. This side has a total of 2 moles. And you're only looking for gases because they're the only thing that is phase that's going to exert pressure. So if we increase the pressure, which way is it going to go? Since increasing is going to go to the side with fewer moles of gas, we're going to go to the right towards the products. That is correct. If you decrease the pressure, you're going to go to the side that has more moles, exactly. So this for this reaction, it's going to go towards the reactants, the side with more moles. So decreasing the volume essentially is telling you what's happening to the pressure. Pressure is increasing here, so basically it's going to go to the side with fewer. So it's going to go to the right. Increasing volumes telling you what about the pressure? Pressure is decreasing, so it's going to go to the side with more moles. And look here, neon, noble gas, inert gas. So this one's going to be a no change or no shift. That happens too. The Haber process. This is more not necessarily needed for particularly answering on a test question, but knowing that what is the purpose of Le Chatelier's principle in general, because lots of reactions are reversible, and in industry, they're going to want to maximize their amount of reactants or ingredients that they're putting in. And we know that making ammonia is very important for fertilizer. So there is a huge, process here where they use lots of machinery to manipulate the reaction to get the maximum yield of the ammonia on the other side. So here is one little diagram. Bigger diagram shows the nitrogen and hydrogen going in, okay? Those would be your reactants. And it goes through a series of, like being through the heat exchanger. It goes through mixing with the catalyst, which we're going to address in a moment, but catalysts help speed up the chemical reaction. And lots of different things to ultimately get the ammonia on the tail end coming out in liquefied form. But yes, definitely a huge process. Just wanted to point that out. And also point out the types of yields that you get here. Even with the best manipulations using Le Chatelier's principle. And I know in the video he said 200 and 450 for the temperature, 200 ATM. But this graphic from textbook says basically the best conditions to get the maximum yield is about 500 ATM and 400 degrees Celsius. But if you look at that, it's still only 60.6%. So that's still not it's not near 100 at all. But this would be a reason why, this concept is used in actual real life applications. Catalysts, how do they affect the equilibrium position? Well, basically, they don't. They lower the activation energy for both directions. And we'll get into the energy diagram again for kinetics, but if you remember from Chem 1 and from last unit, Unit 6, we discussed the reactant heat line, what's in the bonds of the reactants, that goes all the way up to the top of the activated complex. This is what we call the activation energy, or EA. That is the amount of energy needed to get it started. Well, basically what the catalyst does, as you see on the green line here, it lowers the activation energy. But it does it in both directions, whether you're going forward or whether you're going reverse. So it basically speeds them up equally in both directions and has no effect on the K value or the position. So when a catalyst is added, equilibrium is achieved faster, but the equilibrium position and constant K remains the same. So the only thing, once again, that still affects K, changes K, is going to be temperature. Everything else is going to put it back to its same proportion. Now, speeding it up in both directions for a catalyst isn't going to change the position. You're still going to have the same concentration of reactants and products that remain constant at equilibrium. But some of our other disturbances do change the position, where you get different concentrations. But it's still, if it's not a temperature thing, if it's a pressure or a concentration one, those manipulations are still going to yield the same K. So now we're going to look at the graphs. The graphs are fun, and they always ask graph questions in the multiple choice. But a lot of times people have trouble reading the graphs correctly to understand what they're really looking at in the reaction. The first graph over here is with regards to temperature. And with temperature, you should notice that the changes are pretty gradual. It's not a complete spike up or down. Okay, so pretty gradual in its, right here, it's kind of like sloping down. For our reaction where A is going to AB here, this one looks like, since heat is over here, exothermic, and temperature is increased, that means it's going to go left towards the reactants. And as you notice in your graph, the reactant is increasing, the product is decreasing there. The middle graph shows a concentration change. And what you're going to notice about the concentration change ones is only one of the chemical species has a sharp change or a sudden change. Here, the A looks like it's been added. Okay, if you add an A here, you'll notice, okay, it's going to shift towards the products as you see there. So that means some of the added stuff gets consumed, so you see it slowly decreasing there. But your products, of course, since it's going right towards the products, is going to increase. The last type of graph here shown is the pressure graph. pressure basically shows abrupt changes for all of them. They're all big changes. So here we see AB going up, we see A going up, okay, initially, before it gets back to equilibrium. So if this is 2 moles right here, and this is 1 mole, okay, it looks like they must have, what, increased the pressure? Yes, so going to the side with fewer moles, that's why you see a larger jump for the AB there, and a slow decrease of the A. So to sum it all up here, again, temperature changes are going to be gradual, which is the left graph. The middle graph, the concentration change, is going to only show one of the species having a sudden change. The right graph, which is the pressure volume change, because remember you can manipulate pressure using the volume since we have Boyle's law, you're going to see all species have sudden increases or decreases. And if you take a look at these, you'll be able to interpret and read these graphs a little bit better. All right, so our first multiple choice question. Here we have this scenario. They give you the reaction above. H2 plus I2 gives you 2 hydrogen iodide. They show the partial pressures in these graphs, okay, as a function of time, and at a certain time t, extra I2 is added. So which one is going to represent what it's going to look like to get back to equilibrium? Our scenario is adding in I2. Okay, so we know we're looking for a jump in the I2. But where is I2? It is a reactant. If we add in reactants, which way is it going to shift? It's going to proceed towards the products, right? So initially the I2 should spike, but then you're going to see it do what? Decrease. So that puts us here at either A or B, because you need to make sure you get the right I2 there. Then you look at the rest of the reaction up there. We're proceeding towards the products. The HI should do what? Increase. Well, guess what? They're both increasing, so that one can't really tell. But the other reactant, H2, what do we see there? It's a reactant, so it's proceeding towards the products. That means it should be decreasing because it's being consumed. So that's going to put us here with the one that's decreasing. So it should be B. Exactly right. Now for a larger equilibrium graph. We're still using the same reaction though. And we're going to incorporate a few other of our equilibrium concepts in here. So take a moment to see if you can answer these. We'll come back in just a moment. How many seconds did it take for the system to first reach equilibrium? 10. About 10, yes, that's where we see it start to do what? Where it levels off and remains constant. Now, they could also ask this question in the graph. They could ask it in the particle diagram as you saw in the problem set, but they could also give you a table of values where it starts remaining constant. That's where equilibrium begins. All right, so about 10 seconds here. What is the value of Kc when equilibrium is first reached? It is 64. Hopefully you looked and did your equilibrium expression first. So to make sure that you're plugging in the correct numbers. And here the top line is at like 6. Okay, so we do 6 squared on the top. Over, remember H2 and I2 both have the same mole number in front of the reaction, so their lines are together. One's like the dash and the other one is the solid there. And that's around at the first equilibrium position about 0.75 for both. So you could just square that, or you could just multiply it like this, where you're going to get your 64 for your K. Now, since K is 64, what is favored at equilibrium, the reactants or the products?
Products, because
K is greater than 1. Yes, it's going to be product favored, or the equilibrium position lies on the right. You could say that. Yes.
64 is like much greater than, so like if you do still like, it's much greater than 1.
No, much greater is, if you're going for the ones with the extent of K, they're going to be like times 10 to the 5th, like in the thousands. 64 is not really considered that high of a K. All right, so 10 seconds, 64, products, K is greater than 1. Looking at C, we have what happens to the system at 20 seconds. Right here, we notice we've got issues going on, things are changing. So what happened there? Yes?
HI was added, like the products were added.
More products were added?
Oh no, oh my gosh, I removed.
The products were affected, but they were moved, yes. You see the dip here? So that's correct. So we removed some of the HI. It is removed. Very good. Because it took a dip, but you notice when you removed some of the HI that it started to slowly rise after the dip, because it is going to proceed towards the products to start making some more HI. That's why you also notice down here that the two reactants have taken a dip as well, because they're being consumed. Now, for exo or endo here, at 35 seconds, it tells us we increase the temperature. So T goes up here. What you should notice right around there, what happens to our products? Their amount goes down. We're losing products and gaining reactants. So, which way is it proceeding when we disturbed it with the temperature? It's going left towards the reactants. That tells us that adding in heat is happening on the product side. So it has to be exothermic, because adding in the heat made it shift or proceed towards the reactants. Therefore, we can see that. And what happens to our K value here? You see here the HI and the reactants, it's narrowing. So you could actually calculate it if you want to. You don't have to, like you could go with what? This is what? Like, no, this is like 2.75? 2.75 there, and then up here it's a 1.5. You could recalculate it, but you will notice that your K number is now lower, smaller. Or you could just do this as well, noticing that the products are going down, the reactants are going up. Dividing a smaller number by a larger number is now going to make K smaller. One other thing before we move on from this graph, just to show you, like I said, this number, if you did the calculation, is going to be smaller. However, the second position on here, right here, where all we did was take away some of the HI, we calculated the K. This is about 4.8, and down here this is about 0.6. If you do 4.8 squared over the 0.6 squared, what number do you get? It is still 64. So, what it's telling you basically off of the graph here is that the only thing that's changing the K is the temperature. So removing or adding is just going to make the positions change, but when you do the calculation, your K value will be the same. All right. Next graph. At 4 minutes, what's happening here? I think we're good with the graphs now, so you can tell me. What's happening at 4 minutes here? What's going on? Is it concentration?
Yeah.
What kind of changes do we see going on? They're all pretty gradual, right? Going up, going up, going down. So it's some sort of temperature change, but which one is it? Are we increasing or decreasing? What do we need to look at for that? Delta H. Delta H is positive, so where is the heat located? Heat is going to be a reactant since it's endothermic. Delta H is positive, it's automatically endothermic. So if we're increasing, which things are in, which entities, chemical species are increasing? The reactants or the products? Products are increasing, so we know which way it's shifting. Which way is it shifting? Right towards the products. So that means temperature is what? We're increasing temperature because heat is a reactant, because we know it's endothermic due to delta H. It's going to go right towards the products. We know the products are increasing gradually. We also see the reactants are gradually decreasing there, which is the COCl2. What happens at 10 minutes here?
CO is removed.
CO is removed. You see a dramatic change here for that one. The other two are gradual. And remember, when it's a concentration change, it's going to only have one sudden change. Okay, so we have the CO being removed. The last one, probably the trickiest of them all. It is a pressure change. However, which kind of pressure change? Are we increasing or decreasing pressure? We have 1 mole over here. We have 2 moles on this side. So, which way is it going? To the side with fewer or more moles? It's going to the side with more moles because our 2 products are increasing and the reactant is decreasing. So yeah, if it's going to the side with more moles, we know what happened to our pressure. Pressure went down. Probably due to increasing the volume of the container. Because that's really the way you manipulate pressure. The only other way to manipulate pressure is to actually add more particles or remove particles. And as you can see, nothing else was added at this point. All right, we're going to talk about the rate graphs. All right, so the first thing you should have noticed about this one is it is a rate graph. On our Y, we have rate. We do not have concentration. So now we're looking at this other definition of equilibrium. Remember where we're going for equal rates, forward and reverse, going the same rate, same speed. Now it says what stress has occurred in the system, label the graph with what is happening at each stage. Okay, so here was the first equilibrium position for rates. Okay, where they have equal rates. So this is our first equilibrium, equal rates going on there. Initially, the forward is slowing down, the reverse is gaining speed. That's what it's showing you here. This one is slowing down, slowing. This one is going faster as it goes up, like so. So that gets us to our first equilibrium position. Now what do we know about our reaction up here? 2AB gives us 2A and B diatomic B, and our delta H is 26 kilojoules. What does that tell us? This is endothermic, that means heat is over here. We're reading our graph correctly. Which one, the forward or the reverse, increases their rate initially? Which one is higher initially, the forward or the reverse? If you look here, the forward is initially higher, so what does that mean about the direction it's going? It's going towards the products, right? And what does that tell us about what's happening to this? What is actually capable of changing the rate? Temperature. So, what's going on here? Temperature has been increased. Now, if the temperature had been decreased, basically your new equilibrium rate would be somewhere down here, right? It would equalize and be down there because the particles are going slower. At the decrease though, the reverse rate would be higher initially than the forward, okay? So temperature was increased, endothermic's forward rate initially higher until both directions get to the equal rate. Last graph here. It's a rate graph still. At time t here, what's happening? What is responsible for this change? For this particular system that was at equilibrium? Yes?
For example 4, wasn't there a second change on
Second change on the
this graph?
graph for example 4.
Yeah.
We'll come back to that in just a minute. What's going on here? We see that the rate is changing. Rate is now going up here, okay? Rate has increased. But do you see either the forward or the reverse initially being higher than the other? No.
Equilibrium's the same. The K value's the same.
Yes, the K value is going to be the same, but what is making them just both start going faster? Yes, that would be the catalyst. So here in this one, this graph is showing you that a catalyst has been added. Catalyst was added, both reaction rates have increased equally.